Okay. So I hope all of you can see the presentation. Please confirm this now. Hello?
Yes, sir.
Yes,
Okay,
sir, we can see it.
thank you. So before I start the technical discussion, I should like to have a little discussion about the broad nature of the course. So this is your, incidentally, the session is being recorded. You should all keep a watch on a recording tab on the top left column. I hope you can all see it, the recording tab. Please, one of you, please mute your mic. Krishi Patel, Jayesh Bhai, please mute your mic. Thank you. Right. So the pattern of the course, first of all, the pattern of the course is that, the timetable and the way we shall conduct the course. Let me discuss that first. The timetable says that your electromagnetic theory classes will be held on Wednesdays, like today, from 10:15 to 11:30, 1 hour and 15 minutes. Likewise, on Fridays, we have another session, 2 sessions every week, Wednesdays and Fridays. On Wednesday, as we have now, the classes will be held from 10:15 to 11:30. On Fridays, the classes will be held from 8:30 in the morning to 9:45. So these are the 2 lecture hours, lecture slots that we have every week. And in addition, there is a tutorial session every week. The tutorial session is to be held on Wednesday afternoons, starting from 2. It is my usual practice to continue the tutorial, conduct the tutorial session for no more than 1 hour. So very, very likely it will start at 2 and it will end at, very likely it will end at 3. However, this being the first week, it is our usual practice that we are not going to take the tutorial today. Today we shall just have a lecture, but next week onwards, we shall have a lecture on Wednesday morning at 10:15 and a tutorial on Wednesday afternoon at 2 p.m. So those are the things, and of course, in addition on Fridays, we shall also have another lecture at 8:30. All the lectures and tutorial sessions shall be recorded. You have all been invited to join the class in Google Classroom. So all the material, the lecture notes, such as the one that is being projected to you now, these are handwritten notes. So the lecture notes, the recordings, the tutorial problem sheets, their solutions shall be provided to you through the Google Classroom. Therefore, all of you are strongly advised to accept the invitation to join the Google Classroom. I hope you have understood what I've said. I mean, it's a very simple thing to do. Last evening I sent the invitation, so you should finish, complete the process and join the classroom. So that's the usual procedure that we shall follow. I shall start the classes, the sessions, lectures or tutorials every time by my computer clock. And the recording shall also start immediately, and thereafter it will go on for the designated period of 1 hour and 15 minutes. If you have questions or anything, of course, this is a difficult subject, and electromagnetic, I shall come to the details of the subject soon enough. First, let me just broadly talk about the way we shall conduct this course through this semester. You all joined in the year 2020, last year that is, and ever since you joined, you have not been able to come to the JICT campus itself. That is a little unfortunate because learning is always so much better if you're doing it in person. However, the matter is not of our making, our choice. So as of now, this is the best thing that we can do, doing everything online. Electromagnetic theory is actually a very difficult course. It's an intensely mathematical course. Therefore, you're bound to have difficulties in understanding, and particularly when we are doing it in the online mode. So if you have your questions or anything that you need clarity upon, I would advise you make a note of the questions. You can put your questions in the chat window at the end of the class. I usually keep something like 5 minutes or so to discuss such issues if you have anything. In addition, of course, you can also send me emails. You can raise your queries to me by email and I shall try to answer your queries. So that is the one thing. It would be best not to interrupt during the class because it really doesn't serve any purpose. It will just cause some confusion. I regret that it has to be done this way because ideally you should be clarifying things. If you have a doubt on anything, you should be clarifying them immediately. You should be able to clarify them immediately. But well, given the online nature of the course, we don't want to cause too much of a confusion. And so that is one thing. So that is the way we shall regularly conduct our classes: 10:15 on Wednesdays, 8:30 on Fridays. Those are the lectures, and tutorials at 2 p.m. on Wednesdays. And we shall start the session going by my computer clock and go on for the designated or the allocated time. So that is one thing. And of course, as I mentioned, you'll be supplied the study material, notes, tutorial sheets, solutions of tutorial sheets, and the lecture recordings. So that's one thing. On your side, I urge you to do the following few things. You maintain a proper notebook for electromagnetic theory, because there are various things as we go along. You would do well to write them down and understand, because this is not a philosophical subject. This is a mathematical subject. You have to do things by yourself. So it's best that even as you are being shown the notes and the points in the notes are being discussed, you would also do well to work things out alongside. The tutorial sessions will require such things to happen. You will have to work these things out during the tutorial sessions, and then you will have to check with the answers that will be provided to you. That is the usual practice. The tutorial sessions are important because, in fact, they're very important, because that is where you shall be able to have a clear understanding of the nature of the mathematical problems that you'll be asked to solve. So I urge you all to be very attentive during the tutorial sessions, which we shall start next week, not this week, and maintain separate notebooks, work out all the problems. So that's about the general approach to the subject, the practicalities. Now let us discuss a few other things. Someone has raised a hand. You have a question to ask? What is it? Why don't you put it in the chat? I think instead of asking me, put it in the chat. Or perhaps that should be helpful. Yes. Okay, so anyway, so if you have raised a hand, I advise you, instead of raising a hand, put it in the chat and I can give you the answer now. Okay, so now the other thing is that what about the evaluation component and various things like that? See, I haven't gone through the academic calendar very carefully, but I think there are at least 2 examinations, or probably 3. We were asked to submit information regarding the examination, and this course is being taught for 2 separate batches. of the same class of 2020. So Professor Mukesh Tiwari is the other teacher who's teaching this course. So he and I are jointly conducting this course. The tutorial will be common, everything will be common. And so will the exam question papers. And so whatever be the number of exams conducted, either 2 in-sem exams and an end semester exam, or 1 mid-semester exam and 1 end semester exam, whatever be it, we shall go through all the examinations. And the total marks over all the examinations will be 100. So it could be if you have 2 in-sem examinations, some part will be kept for the in-sem, some marks will be. So for instance, if it's a 2 in-sem examination, maybe it will be something like, let us say, 20 and 30 for the 2 in-sem examinations, and the end semester examination will have 50. I mean, that's just an example I'm giving you. The actual mark allocation will be decided upon later. I'm just giving an example. Or if you have a mid-semester examination only and an end semester examination, then probably it will be distributed 40-60. So the exact final distribution will be decided upon later. I'm just giving you these examples. So whatever it is, you will have to get, I mean, you'll have to appear for 100 marks worth of examination. All of 100 marks will be allocated for examination. Your grading will be based on how you perform in this 100 marks paper. I mean, this is electromagnetic theory, so it's a full examination-based evaluation. We don't have any such things like, you know, projects or quizzes or assignments, nothing of the sort. So that is one thing regarding the examination. The exam questions will be numerical in nature, predominantly numerical in nature. As of now, I can't guarantee that it will not be otherwise, but my expectation is that, going by the usual experience, particularly of holding online examinations, predominantly numerical in nature. And it is for this very reason that I told you that the tutorial sessions will be important. Therefore, you attend the tutorial sessions starting from next week with full seriousness. So the tutorial sessions is where you shall learn how to solve all these problems. So they are not going to be very easy, be it assured. Okay. A few things about the grading. Although the final decisions will be taken later, all final decisions regarding the grading will be taken later, but tentatively, I'm saying that you will be graded on the basis of 100 marks that will be there in the examinations. Okay, number one. Number two, if you want a AA grade, the highest grade, you will, in an absolute sense, have to get 90 out of 100. 90 out of 100 in an absolute sense you must get. 90 out of 100. So that's an absolute yardstick. So if nobody in the class gets 90, then very, very likely we shall come to the decision, take the decision that nobody will get a AA grade. So AA grade is the highest grade, and you have to show that your merit is worth that grade. So that's one thing. Similarly, at the other end, to pass the course, if you get below 30, you shall very likely fail in the course. So the thing is that you have to get 90 to get the highest grade, and you shall have to get 30 out of 100, 90 out of 100 to get the highest grade, and 30 out of 100 to pass the course. I'm just giving you proper clarity on these things. Although officially these things are tentative, but this is very likely going to be the outcome. Okay, so I hope you have understood, I mean, how we shall grade the middle grades and those things. Those are a matter of details thereafter. I'm just talking about the pass grade and the highest grade. So on those two things, you will very likely have an absolute yardstick to overcome. Okay, those are the points that I wanted to make. If you have any further questions, you may ask the questions in the chat box. So roughly, I have discussed the basic principles that are necessary. This is going to be a course where we shall have lectures and tutorials. Attendance in the tutorials will be extremely important. I mentioned to you, I've also told you when you shall have your lectures and tutorials, how you should approach the lectures and the tutorials. Keep noting things. Writing will make your understanding more perfect. Tutorial sessions are important because that is where we shall have a discussion on the numerical problems. Your examination, I told you, will be a 100-mark examination paper. I also have informed you that tentatively to get a AA, you must get above 90. Getting above 90 doesn't guarantee you a AA. For instance, a large number of students in the class may get above 90. In that case, what do you do? Well, in that case, the bar for the AA grade will be set higher. But if nobody gets above 90, then nobody will very likely get the AA grade. And similarly, for passing at the other end, you have to get 30. So those are the points I made. So if you have further questions, you can ask me those questions in the chat box. So I have spent some time discussing the basic practical aspects of this course. So with that, we shall now start the technical discussion. Here, I hope all of you can see the presentation and you are all able to hear me clearly. If not, then verbally. For this, you should verbally inform me, interrupting the class. Don't write it because as I'm presenting, I can't see the chat box. My attention is will be focused only on the presentation slide. So verbally inform me if you are unable to see the presentation. So before I start, once again, I ask you to please confirm that you have heard me clearly so far and you can see the presentation. Can a few of you please confirm? Hello?
Yes, sir, you are.
Yes, sir.
Okay. Thank you very much. All of you may now mute your mic. Please mute your mic. Let us not have any distraction. Please mute your mic. All of you, we shall begin the technical discussion about the course. Okay, so this is the course of electromagnetism. For the time being, I shall supply you the notes. There will also be a textbook to follow. It's a very famous textbook written by David Griffiths in the classroom. I shall, in a few days, I shall also upload the textbook. But my advice to you is that for the derivation of various things, this is going to be a very difficult mathematical course. So for the derivation of various concepts, mathematical derivation, rather than focusing on the textbook, you would be better advised to focus on the notes. The textbook will be there, and we shall also, both Mukesh sir and I will also inform you of the relevant portions of the textbook from where you should read, but those things will happen sometime before the examination. As of now, you follow the notes, which shall be uploaded in your Google Classroom. So the book that we shall follow, once again, I mentioned the name, David J. Griffiths. The book will be uploaded for you in due course of time. The author's name is David J. Griffiths, Griffiths, David Griffiths. Okay, so let's now have the technical discussion. We shall be discussing electromagnetic theory or electromagnetism. So this is one of the fundamental subjects of physics. I mean, there are various fundamental subjects, like let us say mechanics of Newton, or thermodynamics and statistical mechanics, or quantum mechanics. And like all of these fundamental subjects of physics, the electromagnetic theory is one of the fundamental subjects. So basically, I mean, since I'm talking about fundamental subjects, they are not very large in number, the fundamental subjects. The applied subjects are larger in number, but the fundamental subjects are few. Of course, physics started in its recognizable form now with the mechanics or the laws of mechanics set down by Newton, and then electricity and magnetism came along in due course of time. Newton set down his laws of mechanics something like 500 years ago, 400 to 500 years ago. Electricity and magnetism has also had an early start, but the full picture was not known for a long time, unlike the mechanical picture that Newton was able to give. Electromagnetic theory had to wait for 2 centuries for a much clearer understanding. We shall go into that development briefly later. So for the time being, we shall concentrate on the 2 words, electromagnetic, which means that it's combining two phenomena of nature, namely electricity and magnetism. At one point of time, it was thought that they were 2 distinct phenomena, that they were 2 different phenomena that owed their respective explanations to different properties of nature. But gradually it was understood that electricity and magnetism were 2 faces of the same coin, and the name of that coin is electromagnetism or electromagnetic theory. So just to get a little ahead of the story, see, if you look at nature, remember we are doing physics. Be very clear on that. We are doing physics. And what is physics? Simply put, physics is the study of nature. It's a very fundamental subject. How fundamental? As fundamental as nature herself. So if you have to understand nature, you have to study physics. So that's the first of the subjects to study. And then extended from physics, you'll have things like chemistry. Separately, you'll have biology. And now there is the understanding that all the 3 fundamental subjects of nature, physics, chemistry, biology, the so-called sciences, are really, can really be merged into one another. So now you have subjects like biophysics and biochemistry, all these things, right? So we are doing physics over here. And if we are doing physics, the first thing that we shall have to look for is where or what in nature is giving rise to this physics. For instance, if you look at the laws of mechanics of Newton, and while you may be a little surprised as to why do I keep referring to the laws of mechanics, although we are discussing electromagnetic theory, it's because many aspects of the laws of mechanics are relevant to electromagnetic theory, and that is how it should be, because nature doesn't have distinct... Hello? Someone's... Please put a stop to this. Don't cause a disturbance. Someone's unmuted the mic. Okay. So see, physics doesn't have compartments really. I'm sorry, nature doesn't have compartments. It's not like that, we have a phenomenon called electricity, we have a phenomenon called magnetism, and they are separate from each other. That was the understanding historically at one point of time. But then it was realized that no, they are not separate from each other. They really blend into each other under certain circumstances. And similarly for the laws of mechanics, they are not really very different. It's not like that the laws of mechanics have nothing to do with the laws of electricity and magnetism. Incidentally, the person who realized this thing with the greatest clarity was Albert Einstein. During this course, we shall talk about the Maxwell equations. That's considered one of the triumphs of human discoveries or human intelligence. And it was Einstein who extended Maxwell's equations and tried to reconcile them with Newton's laws of mechanics. And then he realized that there was a dissonant compartmentalization, and he dissolved that compartmentalization, and as a result you had this most interesting and intriguing physics that Einstein brought forth. Well, that's a different matter. I mean, I will not get into the details of that. So, uh, but I will indeed touch upon that, because one thing leads to another. Uh, in the natural universe, that is actually how it should be. Nature doesn't have compartments. So one phenomenon will blend into another very smoothly under special conditions. And so that is why every now and then, although we shall be talking about electricity and magnetism, we shall be referring to the laws of mechanics, because the laws of mechanics are relevant in various ways, will have a bearing in multiple ways on our discussion. So, since we are studying physics, and physics is the study of nature, then in order to understand a particular phenomenon, we shall have to identify the physical element that gives rise to that phenomenon. Now, what do I mean by a physical element that will give rise to a phenomenon? Let us try to understand. If you are, for example, if you are studying gravity, gravity is a phenomenon of nature that was also discovered by Newton and set down in precise mathematical terms. What is the force of gravitation as set down by nature? The rule says, or the law says, the law of universal gravitation, it says that the force is proportional to the two massive objects, two masses, massive or otherwise, two masses attract one another. And that is why you have this story of Newton wondering why an apple would fall from a tree and land on the ground. Why shouldn't it go upwards? Why did it have to go downwards? That's, you would think, I mean, it's a very commonplace thing. Everybody, I'm sure many people, I mean, countless number of people would have seen an apple falling from a tree to the ground before Newton. But it was a question that might have struck others also, but it was Newton who raised the question and gave the answer. And the answer is that it is happening because of a phenomenon whose name is gravity. Now, what is gravity is a little difficult to say in very precise terms. You just say that it's a phenomenon whereby two masses, two particles, let us say, two particles attract each other. Okay. If you did not have those two particles, then there would be no gravity. So, the physical element, that's something that exists to give you the phenomenon of gravity, are two particles. And what is the defining property of the two particles that will give rise to gravity? Their masses. For instance, you can look at any object around you at this very moment. You're sitting in your room probably and listening to this lecture. There are so many objects around you. They have different kinds of shapes. Your pen will be elongated. Your computer screen will be flat. I don't know, I mean, your tabletop will be a rectangular flat surface. All of them are experiencing the gravity of the earth. That's why they are stuck to where they are, unless otherwise moved around. That is incidentally bringing in Newton's first law of mechanics. I'll touch upon that later. So all of them have some shape or chemical composition and all these things. So they're all material objects. They're all made up of material particles. But the law of gravitation does not refer to their chemical composition. The law of gravitation does not refer to the shape that they have. They could be like a stick, they could be like a football, they could be like a flat screen or a tabletop, whatever. The law of mechanics simply says that you just worry about the mass, nothing else. And if you have a mass, you'll experience gravity. So, a massive object, anything that has a mass, is the physical element of gravity. So if I were to say, give an example, show me something that gives rise to gravity, you'll immediately show me something by way of an example that gives rise to gravity. What will you do? You will simply just lift any object that you can lay your hands upon in front of you and you say that this thing has a mass, therefore it experiences gravity. So you are holding that thing in your hand. That thing physically exists in reality. That is the physical element of gravity. So the laws of mechanics are all driven by things that have mass. Gravity, the law of universal gravitation is also the same. What are the laws of mechanics? Let me just now discuss those three things, and then, because it's important for you to have a broad understanding of the nature of the subject, to understand the physical element which we shall take up. We are discussing physics, we are not discussing philosophy, mind you. Philosophers sit and speculate on things about which nobody is sure whether those things exist or not. For instance, God. Some people will say God exists. Some people will say, no, there is no such thing as God. Nobody has conclusively shown that here, just like you hold your pen or your computer or your book and say that this thing exists, I'm holding it in my hand. There is no possibility of denying the existence of this thing. Nobody has said, held up something and say that this is God. I mean, an idol is just a representation of God, but the idol is not God. So, you do not know whether nobody is sure whether God exists or doesn't exist. Therefore, questions of God is not a part of physics. It's a part of religion and philosophy. Similarly, mathematics, although we shall be it very clearly understood, although we shall be using a lot of mathematics, we are not doing mathematics here, we are doing physics here. The language of nature has got a certain preciseness and universality when it is expressed in mathematics. Nature comes through very clearly when expressed in mathematical terms. But the study of nature is not mathematics. The study of nature is physics, chemistry, biology. These are the studies of nature. Mathematics, after all, is a philosophical subject. That is why many great philosophers are also great mathematicians. The co-discoverer of calculus, Leibniz, who alongside Newton discovered calculus, was a philosopher. René Descartes, the mathematician, after whom you have who Cartesian geometry is named, you have studied Cartesian geometry, was a mathematician also and a philosopher. Bertrand Russell was a mathematician and a philosopher. Why, you will say? You will say, root 2. Root 2 is a philosophical concept, irrational number. Irrational meaning there is no reason, not rational. But in the physical universe, there's no such thing as root 2. If you have root 2, you will have to provide your answer up to the scale up to which you are able to make your measurement. If I say that you have got an answer root 2, I will say, give me the answer in up to 2 places of decimal. You will say 1.41. I will say, give me the answer up to 3 places of decimal. You will say 1.414. Now, why are you not writing root 2, but instead you're writing 1.414? Because you will be making measurements. There's no way for you to measure root 2, but you can measure 1.4. You can measure 1.41 with a scale, with increasing precision. With increasing precision, you should be able to measure 1.414. But there is a limit up to which you can go. That limit of your measuring apparatus is called the least count. I believe you are familiar with the term. We learned all these things in school laboratory in class 6, 7. These are the classes in which we learn all these things. 6, 7, I think, if I recall all right, the least count of a vernier, the least count of a screw gauge, all these things. What do I mean by least count? What's the greatest precision that you can go up to with the help of that measuring instrument? So with other measuring instruments will have greater least count. A microscope will have a greater least count than an ordinary scale that you have. Your plastic scale, that 1 foot long plastic scale, will only go up to centimeter least count. No, sorry, a millimeter least count. Right. A microscope will go up to a micrometer least count. That's why it's called a microscope. So we are discussing physical reality. And in order to understand the physical reality, we have to identify things that give rise to that physical reality. Meaning that we have to be sure first that that thing exists. Then only we can talk about the physics or the chemistry or the things like that. We don't know whether God really exists or not. That's why we don't talk about God in physics. But we do know that an atom exists. By now we know. That's why we call atomic physics. We do know that large objects like the sun and the planet, they exist. That's why we call the physics solar physics or planetary physics. I hope you're able to understand this point, particular point. So we have to identify the physical element that gives rise to a certain physical phenomenon. And we were talking about gravity as an example, that unless you have masses, you will not have gravity. So if you don't have gravity, if you don't have masses, gravity doesn't exist. Therefore, masses are the physical element of gravity. But masses are generally the physical element of the laws of mechanics. And what are the three laws of mechanics? Let me just quickly go through them. First law of mechanics, all set down by Newton, based on observations earlier made by Galileo. And then Newton himself also made his contribution, and then clearly set them down that every object, meaning that you have to have an object, something that has mass, every body or object, they must have a mass, tends to maintain its state of rest or uniform motion along a straight line unless an external force acts upon it. You'll say, well, I mean, I can understand an object. I can understand an object in a state of rest. Right now, if you look around, you'll see various objects in a state of rest in your room, study room. Or you can see objects in uniform motion along a straight line. If you look out of the window, maybe you'll see a car moving at a constant speed. So that approximates the example of uniform motion along a straight line. So that those things are there. But what is a force? Unless an external force acts upon it, what is a force? I don't know what a force is. So you will say, well, what is a force? Well, according to Newton's first law, force is something that violates the state of rest or uniform motion of a straight line, along a straight line experienced by an object. Okay. Now the next thing, that if you have introduced the idea of a force, I'm telling you all these things by way of showing that these are the same things that we shall apply in electricity and magnetism as well. So if you say that, I mean, okay, what is the force? Now you have asked a different thing. I say that force, as I said, a force is something that overcomes the state of rest of an object or its uniform motion along a straight line. Fine. All right. Next thing, we are doing physics. You've just given me a speculative statement. What is force? Force is this thing. It overcomes the state of rest and uniform motion along a straight line. But how do I measure force? We are doing physics. Once again, we have to make precise measurements. And in order to do measurements, we shall have to go to nature and find, first of all, the thing that on which we have to make measurements. We are not studying ghosts here. Ghosts, some people say that ghosts exist. Some people say, no, they don't exist. So there's no way to know. So therefore, those things are not part of physics. So you have to make measurements. If you have to make measurements, then you have to know what you are going to measure. So what is the definition of a force? Don't just say force is mass into acceleration. You'll say force that overcomes the state of rest or uniform motion along a straight line is proportional to two things. What are the two things? The mass of the object, mass, very important, and the rate at which its state of velocity, its velocity value is changing, time rate change of its velocity value, which is to say acceleration. So unless you had mass, you will not have a force. And unless you have a force, the first law of mechanics, I mean, there would have been no second law of mechanics, there would have been no third law of mechanics. And what is the third law of mechanics? That if object A exerts a force on object B, then object B will exert back a force on object A with the same value, but opposite direction, of course. So every action has an equal and opposite reaction. So you notice something. Unless you had a physical element like an object with a mass, there would have been there would have been no laws of mechanics. And so it is, since we are studying electricity and magnetism, we shall now have to address the question of what are the physical elements of these two separate phenomena, namely, one, electricity, and two, magnetism. What are the physical elements? We have to look, we have to study nature. Physics is a study of nature. And as such, the first thing when we study a particular phenomenon is that we have to look for a physical reason underlying that phenomenon. So we have to see what or who has done something, right? If you're a police detective, that's the way you approach your case. A crime has been committed. And so you will say crime doesn't get committed out of thin air. Somebody would have come and committed a crime, a murder or whatever. And so you were theft, dacoity, whatever. And so these things don't happen by themselves. So somebody in physical presence has done this thing. So you have to look for that somebody, the criminal, that is. And so it is that here we are looking at physical phenomena, and we have to look for the things that give rise to physical phenomena. It was understood that electricity was owed to things that exist in nature called charges. And it was understood and thought that magnetism was owed to things in nature that were called north poles and south poles. A magnetic bar magnet that had a north pole and a south pole. So that was the understanding that held sway. But no, as progression happens with everything, so does it happen with human knowledge. In fact, that's the first thing which progresses. Thereafter, everything follows. Human knowledge progressed to a stage whereby it was realized that electricity and magnetism, although they may appear different to your eyes, but in reality are owed to only one kind of thing that physically exists. And what is that one kind of thing? Charges. Be it understood at this point very, very clearly and carefully that there is no such thing as a north pole or a south pole in nature. All of magnetism is owed to charge particles, just like all of electricity is owed to charge particles. There is no such thing as, in reality, there is no such thing as a north pole or a south pole. How so? We shall discuss all those things later. The person who had the first realization that magnetism is really happening because of an underlying physical electric phenomenon was Ampere. And he said that magnetism happens because of an electric current. What is an electric current? An electric current is simply a continuous flow of charges. If you have charges flowing, you'll have a current. And if you have a current, you'll have magnetism. In reality, there is no such thing as a north pole or a south pole. So that is the most important observation that unifies both electricity and magnetism, that they really are two seemingly different phenomena. They appear to be two different phenomena, but they really are owed to charged particles, particles that carry charge. Okay, so basically electromagnetic theory or electromagnetism is simply put the study of the physics of charged particles, statics and dynamics. Now comes a little discussion on these two words. What is statics? What is dynamics? You have a fixed charge fixed in space. This charge will give rise to electricity. Charges always give rise to electricity. But charges do not always have to give rise to magnetism. You can have charges, but no magnetism. When will that happen? I hope you're listening to me very carefully. This is one fundamental insight about nature. So listen to me very carefully at this point. Charges will always give rise to electricity, but charges need not give rise to magnetism always. It is only when charges are in motion. A static charge will not give rise to electricity. It is only when a charge is in motion that you will get magnetism. So simply put, static charges, electricity, yes. Magnetism? No. Charges in motion? Electricity? Yes, of course. Charges, whether they are static or moving, will always give rise to electricity. But charges, only when they are in motion, will give rise to magnetism. So be it understood very carefully. Static charges, electricity? Yes. Magnetism? No. Moving charges, electricity? Yes. Magnetism? Yes. So magnetism is the consequence of charges in motion. Once again, I stress upon this fact that in reality, in nature, there is no such thing as a North Pole or a South Pole. The physical element of electromagnetic theory is the charge. Just like the physical element of gravitation is the mass. The physical element of the laws of Newtonian mechanics is the mass. If you think about it carefully in nature, there is really nothing much else. Particles have mass, particles have charge. What else do they have? Not much else besides. So basically, well, you are students of ICT, Information and Communication Technology, but that's a branch of engineering. It's a new branch of engineering, but very old branches of engineering, like let's say mechanical engineering or electrical engineering. Mechanical engineering is older than electrical engineering. What are the concerns of a mechanical engineer? To study the properties of masses and make use of those properties to develop technology. Simply put that way, nothing else. Design a pulley, a lever, I mean, all of these things, whatever a mechanical engineer does, the fundamentals we have studied at school already. Thereafter, it's just doing things with a little more refinement and stuff like that, dropping something, making something else go up. For instance, in a lift, a weight goes up, the lift comes down, like a pulley mechanism. Or the weight goes down. You would have seen this thing happen in a lift, maybe in old-fashioned lift, not in these new lifts where you have steel doors closing shut. You can't see anything, and the lift is also closed from all sides. But if you see lifts with collapsible gates in old buildings, you'll see this thing, weight going down, lift going up, lift going down, weight going up. Just something that is studied. So these are properties of masses. You're making use of the laws of mechanics on things that are physically massive. Just to give you an example, or you have automobiles engineering, rocketry, all these things. These are various branches of mechanical engineering that have become specialized. So basically, engineers, what do they study? If you were a mechanical engineer with all its sub-branches, you'll be exploiting the properties of masses through the laws of Newton's mechanics and stuff like that, and then other laws that followed, derived laws. And similarly, if you were an electrical engineer, what will you do? You'll exploit charges. What will you do? You'll generate a turbine and a generator. That incidentally combines both mechanical engineering and electrical engineering. You try to generate electricity, all sorts of things. So basically, these are the two things that really exist. So I mean, if on quiet reflection you realize that everything else really is just building around this fundamental core. Mechanics and electromagnetics. An engineer, mechanical engineer, is interested in the former, and electrical engineer is interested in the latter. For the former, the physical element in which a mechanical engineer is interested are massive objects, masses. For the latter, that is to say an electrical engineer, the physical element in which he or she is interested are charges. So nature, the kind of things that we see all around going us are largely owed to only these two things. Largely, but not completely. I'm not going to get into the discussion on the exceptions. They are pretty complicated, but largely owed to these two things, masses and charges. So the question is then, what is a charge? I've been talking about charges, and I said that this phenomenon of electromagnetic theory, electricity and magnetism, is owed to something that physically exists. And what is that something that physically exists? It's a charge. You'll say, well, I mean, what is the proof that a charge exists? I say, put your finger in an electric socket and then you'll realize that charges exist. Right. You'll say, what is the proof that masses exist? I'll say, I'll throw a hard object at you on your back or on your head, and you'll feel very well for yourself the existence of masses. Would your finger touch a live electrical wire? Hello? Please don't, please don't create a disturbance. Otherwise, I'll have to mute you. Yes. So, what is the proof that a charge exists? I'll say go and touch a live wire and you'll experience for yourself what a charge is like. So, charges exist in reality. Right. Okay. Then you tell me, I ask you, you can ask me or I can ask you, what is a charge? Now, that is a very difficult question to answer. You'll say that, okay, I mean, there is something that will give you a bad shock when you touch a live electrical wire. I mean, why should it give you a bad shock? Because charges are flowing through that wire. Okay, very much. Now, if you touch a wire, then the charges will find a different outlet through your fingers and move into your body, and you'll get the shock. Right. So charges exist, but then the next question is how to describe a charge. That is a very difficult question. You see, in nature, once again, we study nature. But nature appears to us in different layers. Layers, layers. On certain layers, we see nature differently than at certain other layers. For instance, if you look at a glass of water, maybe you'd want to have a drink of water. You see a glass of water. What will you see? You'll see a clear liquid in the glass. It's sloshing around, moving around. All that thing. You can drink that liquid. But is it really a liquid? You will ask me what a strange question to ask. I said no. But if you think about it, liquid is something that is continuous, flowing. There is no gap in liquid, continuously flowing or continuously distributed. But is it really a liquid? Because if you go deep down, and this is something we have realized by now, although we haven't seen it with our bare eyes, I said nature appears to us in different layers. If you just look at a glass full of water with your unaided eye, you'll see a liquid. But if you look at the glass of water through an extremely powerful electron microscope or something like that, or whatever, you'll see that it's not really liquid, continuum distribution, but you have discrete, granular, distributed objects called H2O molecules. You have one H2O molecule, then some empty space, then you have another H2O molecule, like that. So from different points of view, you will see nature appear differently to your eyes. The same thing will look different from different scales of observation. But then there is a certain fundamental scale, fundamental perspective below which you can't go. Incidentally, rather than water, you can think of the example of sand. Gujarat has got a large part of desert. Many of you are from Gujarat, probably, or Rajasthan, our neighboring state. So this has got a large part of desert. In a sandstorm or in a strong wind, you would have seen, or at least you would have seen in photography or a video recording, that the sand is moving like it were a continuum. The waves of sand, we say. Sand dunes, they are in motion. It's almost like a liquid motion. But even with so if you look at it from a distance, the sand would look like that, it's nice wave-like thing going on in strong breeze, strong wind. But if you look very up close, lift a little amount of sand in your hand and look closely, it's just, it doesn't look like a liquid at all. It looks like a collection of grainy particles. So as you can see, seen from a distance, it will look like a continuum distribution, but seen up close, even with your bare eyes, you'll see grainy particles. And so it is. This is the idea that we can bring to bear upon this question of what is a charge. I really don't know. Nobody really knows what is a charge. You just say that deep down, if you go, you will have these grainy particles containing something that you call a charge, if these particles move and you touch a wire in which the particles move, some of them will get injected into your fingers and you'll feel a shock. A little shock you can feel occasionally, very small, weak voltage connections in batteries or anything. You'll just see a spark, a mild shock. Of course, if you hold a live wire containing a very large voltage, that will be fatal. So not advised at all. But you occasionally, in our lives, we have all experienced small shocks. On winter day, you open a car door and you'll feel a little small shock. So that's the kind of thing that you experience. So that's a charge. Now, there is a fundamental scale of nature on which charges exist. You'll say you can't really go beyond that. At a certain fundamental point of nature, scale of nature, you'll just have concepts. You can't put words to those concepts. What is a charge? I don't know what is a charge. Nobody has said in so many words that a charge is this, whatever. You can describe so many other things in words. If I ask you to, if I have not seen a car and I've asked you to describe a car to me, you'll say a car is an object which is self-propelled through an engine. It has got a driver's seat, all those things. You can describe a car. Nobody is able to describe a charge because your language, your vocabulary, this point has to be understood carefully and clearly. Your language, your vocabulary, these things are limited by your experience of nature. And nature has not designed you to go down to a scale where charges exist in their full right, separate charges, and which you can use for yourself or exploit for yourself for some purpose or whatever. So that is why when you go down to fundamental scales of nature, which are not really experienced with your senses, you can't really put words to them. You just have to conceptualize them, and you can make measurements about them. You can put a name to them, but you can't really put a description to them. Because ultimately, we shall be talking about fundamental laws, and fundamental laws are the first principles of nature. If you can break down a fundamental law which contains the description of which contains a description of the properties of fundamental objects of nature, if you can break that down in terms of simpler terms, then that doesn't remain a fundamental law. A law is the first fundamental of nature, laws of mechanics, laws of electromagnetic theory. So these are laws that we shall, we shall talk about. So what is a charge? Not a very easy question to answer. As best as I'm aware, no one has been able to put words to it. You just have to conceptualize something called a charge. And then with that understanding, you know that something exists with this name called charges. And then knowing that they exist, you start making your observations of nature. And what are the observations of nature that you have? Observations, how do you make observations of nature? You do so by carrying out experiments. And what is an experimental fact of nature? That charges come in two types only, positive and negative. Positive and negative, and the definition is not absolute. It's a human convention by which you make the definition. And so, incidentally, the definition, the convention was set by Benjamin Franklin, whose face you will see in American banknotes. So, positive and negative charges you have, and you'll find that charges of one type, let's say positive, will repel one another, and charges of opposite type, let's say positive and negative, they will attract one another. So two negative charges, they will repel. Two positive charges, they will repel each other. A positive and a negative charge, they will attract each other. And one last point, I'll take up these points in greater detail in the next class. These charges occur in discrete amounts. And what is that fundamental amount of charge? The value of the charge of a proton plus E amount of charge. An electron will be minus E. And so this will be 2 electron charges. This will be 11 electron charges. So they will always be an integral multiple of a basic irreducible minimum amount. And that minimum amount is the charge of an electron. As our usual experience goes, there are certain violations of that principle, but I don't want to get into that discussion. Anyway, time is up for today. I shall stop the sharing of the lecture. This will be recorded. I hope the recording is on. Yes, it is. So if you have any questions, you can ask me now. Otherwise, we may leave the session. Has anybody put any question in the chat? Nobody has. You can put questions in the chat while the class is going on. Later, we will have more technically intense discussions. Today, we were just establishing the broad principle of the subject. So if you don't have any questions, you may then please leave.
Excuse me, sir.
Yes.
Sir, as you told us that second law of Newton, F is equal to mass into rate of change in velocity. But specifically, yes.
Yes,
But
yes.
specifically, force is equal to